Right, ideal gas law questions are really common in your first year and they're normally worth quite a few marks. We're talking 4 or 5, so that's not something to be sniffed at. These are big mark questions. And you can normally get at least a couple of the marks relatively easily for rearranging the equation and for converting units. If you know the equation and you know the units, that's 2 out of 5 marks, 40%, and then anything else is a bonus. So how do you recognise it's an ideal gas law question? Easiest way, has it given you a value for R? If it has, at least in your first year, it's an ideal gas law question. As soon as you see it's an ideal gas law question, down the side of your page, write P, V, N, R and T. And write down the data given in the question. So we've got 100 kilopascals. That's not in the right units. We need to get that into pascals, so times by 1,000. Because just like kilograms into grams, you times by 1,000. So 100 times 1,000, stick on 3 more zeros. They've given us a volume. Nope, that's what we're trying to work out. Number of moles, they haven't given us either. R is 8.31 and the temperature is 60 degrees C. We want that in Kelvin, so add 273 and you end up with 333 Kelvin. We've got 1 mark just for the conversions there. Now, we've got these 2 gaps. One for volume, which we know is what we're trying to work out overall, and the other one for number of moles. We can't work out volume unless we know the number of moles. So there must be other information in the question to work out the number of moles. And let's see what other information they've given us. We've got this mass here. 3.74 times 10 to the minus 2 grams of the magnesium nitrate. It's completely decomposed by heating, and we want to work out the total volume of gas. So the gases in our question are this nitrous oxide and oxygen. We don't know anything else about that yet, so we can work out the magnesium nitrate, or the number of moles of that, and then do the ratio to work out the number of moles. It's just a reacting mass calculation before you go into the ideal gas law. So to work out the number of moles of the magnesium nitrate, we've been given a mass, so the equation we're going to have to use is number of moles equals mass over molar mass. Therefore we need to work out the molar mass of the magnesium nitrate. So again, I'll write down what I'm working out the molar mass of, just to make it really clear for the examiner what I'm doing. Now I've got magnesium, which is going to be 24.3. Add, now the next bit's in brackets, so it's going to be 2 times something. Nitrogen, which is going to be 14. And I've got 3 oxygen, so I need to do 3 times 16 for the oxygen. And you end up with a molar mass of 148.3. And again, write it down. You might get a mark for it. / you will. So now I can actually work out the number of moles. The mass, 3.74 times 10 to the minus 2, which is in the question. Don't forget the minus, that's quite important. Divide by the molar mass I've just worked out, and therefore the number of moles is going to be 2.522 times 10 to the minus 4. Now that is my moles of the magnesium nitrate. Next step is to do the ratio. So the number of moles of magnesium nitrate, let's pick a new colour for this, shall we? Let's do it in orange because that's always exciting. I've got a 2 there, so the first part of my ratio is going to be 2. And then what am I going to? I've got a 4 and I've got a 1. So this is going to be 2 and I'm going to 4 plus 1, which is 5. So my ratio is 2 to 5. So my number of moles of gas in total, this is why it's really important to look at the state symbols and see how many gases have you got, is going to be the 2.522 times 10 to the minus 4. Again, try not to round that number too early. Multiplied by whatever you're going to, which is the 5, and divided by whatever you're going from. So times 5 divided by 2, because I'm going to 5 moles of gas coming from 2 moles of the magnesium nitrate, and that gives you 6.305 times 10 to the minus 4. When the decimal point is obvious. Now you can always think, have I done this the right way round? Should I divide times by 2 divided by 5, or should I have done 5 divided by 2? Well, if you think you're going from 2 to 5, my number must get bigger, and my number of moles has gone from 2.5 times 10 to the minus 4 to 6.3 times 10 to the minus 4. It's got bigger. I've gone the right way. Now, that 6.035, that is going to be the number of moles that you can now pop down your data at the side. So now you know everything in the ideal gas law except for one thing, so now you can do the ideal gas law. So we know the ideal gas law is PV equals nRT, and therefore we can rearrange that by just dividing both sides by P. So V equals nRT divided by P. Now we want to substitute all our values in. And again, it's worth, if you've written this down the side, then they know that you've done all the conversions right. If not, you can have all the conversions right when you rewrite the equation out in full. Times 10 to the minus 4 times the 8.31 times 333. Divide all of that by pressure. This is where you mess it up because you don't put enough zeros into your calculator, and you end up with 1.745 times 10 to the minus 5 meters cubed. But the question asks it for in centimeters cubed. So if you think of a cube, not my finest drawing ever, but hey ho. So this is a 1 meter cubed. Every side is 1 meter long. If I want to convert that into centimeters cubed, that side now becomes 100 because 1 meter is 100 centimeters. That side becomes 100 because I have times by 100. That one is also 100. So to go from meters cubed to centimeters cubed, I have to times by 100, times by 100, times by 100. Now that is times by 10 to the 6 or times by a million. And that will give you 17.45 centimeters cubed. And that is your total volume of gas. You can draw that cube and work out the conversion anytime you want. So now if we think about what our marks are for, we have worked out the number of moles, 1. We've done the ratio to work out the moles of gas, 2. We've done our conversions, 3. We've rearranged the equation, 4. Popped it all into the equation and then done the final conversion, 5. That's what your 5 marks are for. So if you write down all the PV nRT down the side, you can then see what you need to work out, and therefore you can see, do I need to do a reacting mass calculation beforehand to work out the number of moles? Quite often you do. If you don't have to do that, they'll do it the other way around, where you do the ideal gas law and do the ideal gas law at the end. Good luck.